Hello, welcome to Zono Academy. In this video, we continue looking at dimensional analysis. In the previous video, we had established one use of dimensional analysis, which is to determine the units of physical quantities. In this video, we shall look at how to check the homogeneity of an equation using dimensional analysis. So in this video, we focus on looking at the checking of the homogeneity of an equation. Checking of the homogeneity of an equation, this just simply means an equation is said to be homogeneous if at all the dimensions on the left hand side are the same as the dimensions on the right hand side of an equation. Then an equation is said to be homogeneous. So when we are checking for the homogeneity of an equation, we are simply trying to see whether the dimensions of any equation, any fundamental equation, has the same dimensions on the left hand side and the same dimensions on the right hand side. Now, in order to do that, there are some simple or basic rules that I have established that will be helpful in carrying out this process. So I'll run you through these simple rules that you can follow in checking for the homogeneity or checking whether the equation is dimensionally correct. So an equation is said to be dimensionally correct if at all it has dimensions on the left hand side the same as dimensions on the right hand side. In other words, if an equation is homogeneous, then the equation is dimensionally correct. So what we will be doing in this video is to check whether the equation is dimensionally correct by simply checking whether the equations on the left, the dimensions on the left hand side are the same as the dimensions on the right hand side. So simple rules that you can follow that can guide you in establishing whether the dimensions on the left hand side are the same as the dimensions on the right hand side are as highlighted here. So the first simple rule, which entails that the equation is dimensionally correct, as I have already stated, is when the dimensions on the left hand side are the same as the dimensions on the right hand side. So if you are able to prove that the dimensions on the left hand side are the same as the dimensions on the right hand side, then that simply means that your equation is dimensionally correct. And I will explain this one by one in just a short while. And the second simple rule that you should take note of is that for addition and subtraction to occur within a fundamental equation, the quantities that are being added should be quantities with the same dimensions, or the quantities that are being subtracted must be quantities of the same dimensions. And I will explain this also in a short while. The third simple rule that can guide us is that dimensions also can be treated just like any algebraic quantity. So they can be treated as algebraic expressions or algebraic quantities, and I will explain also what that simply means. And the fourth simple rule that you can follow is that any pure number or any constant, unless stated otherwise, are dimensionless. And by dimensionless, this just simply means that dimensions are equal to 1. So a pure number has dimensions equal to 1, I'll explain that, and a constant has dimensions equal to 1, or simply put, they are dimensionless. And the fifth simple rule that we have established that can guide is that the dimensions of the argument of the trig ratio of the trig ratios are dimensionless, or that they are equal to 1. And so let's see what this simply means for each one of them. So let's take them one by one and try to establish these simple rules. Let's try to explain these simple rules. So the first rule, as I have already stated, is that dimensions on the left hand side must be the same as dimensions on the right hand side. So if you have a fundamental equation which has quantities, physical quantities, so let's say a physical quantity A, or any quantity being represented by A, this could be a distance, it could be velocity, or any physical quantity as we have looked at in the previous videos. So let's imagine this A represents a physical quantity, and there is an equal sign to show that this is an equation, and it has other physical quantities after the equal sign. So for this equation to be dimensionally correct, or for this equation to be homogeneous, we are saying the dimensions of A on the left hand side must be the same as the dimensions of B. So the dimensions that we get on the left hand side of this physical quantity and the dimensions that we get for this physical quantity on the right hand side, these must be equal, or they must be the same for that equation to be dimensionally correct. And that is what rule number 1 simply means. So if you are able to check and you see that the dimensions on the left hand side and the dimensions on the right hand side match, then that equation is dimensionally correct. And rule number 2 just simply entails that for addition and subtraction to occur, the quantities that are being added or the quantities that are being subtracted must have the same dimensions. So this simply means, for example, as part of any equation, maybe you could have the left hand side with physical quantity A equal to, let's say, B, any physical quantity being represented by B, and another physical quantity being represented by C. So what this simply means is that for addition to occur, for this operation addition to occur, the two quantities that are being added, B and C, must have the same dimensions. This simply means that the dimensions of B in this case must be equal or must be the same as the dimensions of C for this to occur. If this is not the case, if the dimensions of B are not equal to the dimensions of C, it simply means that that equation is not homogeneous, or that equation is dimensionally incorrect, because rule number 2 does not hold. So we are saying the dimensions of B and dimensions of C must be the same for addition to occur. Or if this was in the case of subtraction, where C is being subtracted from B, we are saying the dimensions of B, this physical quantity, must be the same as the dimensions of C. That is what rule number 2 entails. And rule number 3 also simply says dimensions can be treated as algebraic quantities. What this simply means, or algebraic expressions if you want to put it that way, what this simply means that all the rules of algebra can be applied on dimensions. What that means is that division, multiplication, and all algebraic rules can be applied on dimensions. So in other words, two dimensions can be divided if they're dimensions of the same nature, or if they're dimensions of the same physical quantity. Dimensions of the same physical quantities can be multiplied. So for example, just an example, if we had length, you can multiply it with another length. So these dimensions of length, capital letter L, dimensions of another length, capital letter L, and this can just result into L squared as a dimension. Or if we had L and T, we can divide through by T, meaning division here will just take place where T cancels out with T, and the final dimensions will just be capital letter L. So this simply means division and multiplication or any other algebraic rules are applicable in dimensions. So dimensions can just be treated as any other algebraic expressions. That is what rule number 3 entails. And rule number 4 simply says that any pure number, any constant, unless stated otherwise, are dimensionless. And like I explained earlier, this simply means the dimensions of a pure number, the dimensions of a constant, are equal to 1. So what this simply means is if we had a physical quantity, for example, A, and it has a pure number in front of it as 2A. So this simply means dimensions of 2 multiplied by dimensions of A. So this, as a physical quantity, will have its own dimensions. So the dimensions of 2, according to this rule, are just equal to 1. In other words, this will just result in 2. So dimensions of 2 will just be given by 1 times the dimensions of A. So basically this will just be dimensions of A. So a pure number or any constant are dimensionless, or they have their dimensions equal to 1. Or in another example, if we had a constant K that has not been stated, or it's just a constant, and we have a physical quantity A. So this simply means that the dimensions of this constant K will just be equal to 1 and multiplied by the dimensions of A. So this will just transition to dimensions of A. This is what rule number 4 means. And rule number 5 simply says the dimensions of the argument of any trig ratios are dimensionless if they are equal to 1. So the trig ratios that we already know are sine, cos, and tan. So we have the sine, the cosine, and the tangent. These are the trig ratios. So when we say dimensions of their arguments are dimensionless if they are equal to 1, what this simply means is that, for example, if you have sine x, so this x here is what is referred to as the argument of this trig ratio sine, or if this was cos, the value that follows after that trig ratio is its argument. So what this simply means is that if you had, let's say, sine, and the argument of this sine maybe is a physical quantity, acceleration, and maybe multiplied by time. So the argument, which is at here, its dimensions will just be given by at, and the dimensions of this must be equal to 1 for this value here, this trig ratio, to be dimensionless. So for it to be dimensionless, its argument at here, the dimensions of its argument, which is dimensions of a times t, must be equal to 1. Then this trig ratio is dimensionless. And if that is the case, then we can just simply replace it by 1, and then our equation will be homogeneous or will be dimensionally correct. And we'll be able to see that through an equation. And I must mention that for an equation to be homogeneous, for an equation to be dimensionally correct, all these 5 rules must work together. So if only one of them is broken in an equation, then the entire equation becomes dimensionally incorrect. So all of them must be satisfied for an equation to be dimensionally correct. Let us proceed into looking at a few examples of how we use these rules in checking for the correctness or dimensionally correctness of an equation. So let's look at a few examples where it says that check whether the following equations are homogeneous, or check if they are dimensionally correct. So in order to check for these equations, we will need to follow the rules that I have highlighted. So let us begin with example number 1, where we have velocity. We have final velocity is equal to initial velocity plus acceleration times time. Now this is a very well-known kinematic equation. So we shall prove that this equation of motion is dimensionally correct, or we shall check if it is dimensionally incorrect using those rules. So the first step that you take is to identify the operator. So by operator, I just simply mean equal sign, additional sign, subtraction sign. Those are all the operators. So in this, you can tell that this is an equation because there is an equal sign. So immediately you identify the equal sign. The rule that comes into your mind is the first rule, that for this equation to be dimensionally correct, the dimensions on the left-hand side must be equal to the dimensions on the right-hand side. Okay? So dimensions on the left-hand side must be equal to dimensions on the right-hand side. So then we first begin by checking the dimensions on the left-hand side. So on the left-hand side, what do we have on the left-hand side? So the first step is to identify the physical quantity. So the physical quantity that we have on the left-hand side is velocity. So whether final or initial velocity, velocity is velocity. Whether at its initial position or at its final position, velocity is velocity. So first thing you identify is that you have physical quantity velocity, or simply put, final velocity. All right. So then the next thing now is to know what are the dimensions of velocity. So you know that dimensions of velocity are expressed by brackets. So you say dimensions of velocity will just be equal to, remember in the previous videos, because velocity is derived from distance and time, so therefore its dimensions will just be L over T. So these are the dimensions on the left hand side. So on the left hand side we only have one physical quantity, which is just velocity, and its dimensions are just given by L over T. Then now we proceed to checking what is on the right hand side. So now we proceed to checking what is on the right hand side. So on the right hand side, you quickly check, you will see that there is initial velocity, but at the same time you have another quantity here. So you have two parts here that are being separated by the operator addition. So immediately you identify the addition sign. Rule number 2 comes into your mind, that for these two terms to be added, term 1 and term B, term A and term B, for them to be added, they must be of the same dimensions. According to rule number 2, the moment you identify the additional sign, it simply means this term here and the term here that is being added to must have the same dimensions. All right, so let me use this as my first term, the velocity. So we say dimensions of V naught, initial velocity, whether at its initial or final position, will just be velocity, meaning the dimensions will just be L over T. All right, so now because there's an additional sign, so we're expecting that even this entire term, acceleration multiplied by time, must have the same dimensions. So after checking for initial velocity, let's now check the acceleration multiplied by time dimensions. All right, so since this can be treated as an algebraic expression, this just is the same as saying dimensions of acceleration multiplied by dimensions of time. So we know from the previous videos that dimensions of acceleration are just given by capital letter L over T squared. Then this will just be multiplied by dimensions of time, which is just capital letter T. Now, because according to rule number 3, these can be treated as algebraic expressions, meaning this multiplication can occur because this is the same base T and this is the same base T. So you have one T there cancelling out with one T there. So you will just remain with L over T. And you can tell that the dimensions here are the same as the dimensions here. So that satisfies condition number 2, that the two terms that are being added, term 1 being the velocity and term 2 being acceleration times time, have the same dimensions. Therefore, there is a possibility that this equation is dimensionally correct, because on the right hand side we can see that it is homogeneous. But we still have to satisfy this condition that the left-hand side must be the same as the right-hand side. All right, so we can see that on the left-hand side, we have dimensions L over T. Now, on the left-hand side, because these two dimensions are being added, so we'll have a situation where we have dimensions of V0 being L over T plus dimensions of AT being L over T. So this will just now become 2L over T. So these are the dimensions on the right-hand side. Now what remains is just comparing the dimensions on the left-hand side with the dimensions on the right-hand side. So in this case, we have dimensions on the left-hand side being L over T equal to dimensions on the right-hand side being 2L over T. Now, because this is a constant or this is a pure number, the dimensions of this will just transition to 1, meaning this just simply becomes L over T is equal to L over T. So you can see that the dimensions on the right-hand side, on the left-hand side, and the dimensions on the right-hand side are the same. Therefore, this equation is dimensionally correct. So it is homogeneous. This dimension is homogeneous because the right-hand side is equal to the left-hand side. Alright, so we have proven that that is homogeneous. Now let us proceed to looking at example number 2. So this is homogeneous. Now let us check whether this equation also is homogeneous or if it is dimensionally correct. So in a case where you are given a question such as that, Vi of V naught T plus half a T squared. So in the equation, you will be told what these quantities represent. So like in this case, Y represents a displacement, Vi represents a velocity, and T represents time, A represents acceleration, and T represents time. All right, so the first thing, you identify an operator there. So you're able to see that there's an equal sign, and rule number 1 comes into mind. So you know that dimensions on the left-hand side must be the same as dimensions on the right-hand side. Okay, so you first check, what do I have then on my left-hand side? Okay, so what physical quantity do you see on your left-hand side? You have a displacement. So Y as your displacement. So dimensions of Y, because this is displacement, which is just derived from a fundamental unit, a fundamental quantity, which is length. So you know that the dimensions of Y will just be capital letter L. All right, so that is all that you have on your left-hand side. So you have length on your left-hand side. Now what remains is to check what you have on your right-hand side. So on your right-hand side, what do you have on your right-hand side? So on your right-hand side, you see that there are two terms that are being separated by the operator addition there. So you have this as your first term, and you have this as your second term, the whole of this, and the whole of that being separated by an operator which is addition. So the moment you identify that there is an addition there, rule number 2 comes into mind, that for the two terms to be added together, they must be of the same dimensions. So let us check the dimensions of the two terms. So the first term that we have is VIT. So dimensions of VIT, because this can be treated as algebraic expressions, this is the same as dimensions of velocity multiplied by dimensions of time. So this will just simply be dimensions of velocity. We know that this is just L over T times dimensions of T will just be capital letter T. So we'll see that this T cancels out with that T, meaning that will just be length, capital letter L. All right, so our first term has dimensions which are just equal to the dimensions of length. Now we check our second term on the right hand side. So on the right hand side, we have half AT squared. So dimensions of this, the dimensions of all this is the same as saying dimensions of half, dimensions of A, dimensions of T squared. Okay, so this just then becomes, because this is a pure number, so dimensions of half, you just have 1. And dimensions of acceleration, you have L over T squared. And dimensions of T squared, we just have capital letter T raised to the power 2. So this T squared cancels out with that T squared, and that 1 times L will just be L. So you can see that our two terms, this is second term and this is first term, our two terms that are being added, our first and second term, have the same dimensions. So there is a possibility of this equation being dimensionally correct because the second rule has been satisfied. However, we still have to satisfy the last rule, which is left hand side must be the same as right hand side. So what do you have on your left hand side? Dimensions on your left hand side, you have L. So capital letter L on your left hand side. So we're saying they must be the same as dimensions on the right hand side. So on the right hand side, you have an addition of the two terms. So the first term has L plus L. So you have L is just equal to 2L. Now because this is a pure number, so the dimensions are just equal to 1. Therefore, the dimensions on the left hand side are equal to the dimensions on the right hand side. This simply means this equation is dimensionally correct or homogeneous. So we have proved using principles of dimensions and following those simple rules that we have highlighted. All right, so let's quickly look at the last example. So we have proven that this also is dimensionally correct. Now we have to check that this is also dimensionally correct. So where you're given an equation which is y is equal to a sine with an argument 2 pi t over t. All right, so in the equation you'd be given that this is the displacement, y is just the displacement, a is the amplitude or maximum displacement, and t is the time, then capital letter T is the period. All right, so let's check that this equation is homogeneous or it's dimensionally correct. Okay, so the principle is the same. The first thing you identify is the operator, which is an equal sign. So this is an equation, and for this to be homogeneous, it simply means dimensions on the left hand side must be equal to dimensions on the right hand side. Okay, so the first thing now is to check what do I have on my left hand side. So on your left hand side you have a displacement, so dimensions of my displacement will just be L. All right, and that is all that you have on your left hand side. And on your right hand side, what do you have? So you check on your right hand side, the first thing that you identify there is an amplitude. Amplitude is just a displacement, maximum displacement. So on your right hand side you have dimensions of a sine 2 pi t over t, which is now just the same as saying dimensions of a multiplied by dimensions of sine 2 pi t over t. So you know that dimensions of amplitude, this is just the displacement, so this would just be L. But on the displacement, on the dimensions of sine 2 pi t over t, so you notice that this is a trig ratio, which is just a sine, and this is only dimensionally correct if this trig ratio is dimensionless. But for the trig ratio to be dimensionless, the argument, the dimensions of its argument must be equal to 1. So let's first check the dimensions of its argument. So the argument is just 2 pi t over t. So we are saying dimensions of the argument of the trig ratio 2 pi t divided by t, right? So this is that. Okay, so the dimensions of this must be equal to 1 if this trig ratio is dimensionless. All right, so 2 pi t, this is the same as saying dimensions of 2 pi, dimensions of time divided by dimensions of the period, which is just also the time. So you know that dimensions of 2 pi, so 2 pi is just 2 times 3.14, so this is a number. So even if you multiply it, it will still be a number, and it simply means that the dimensions of 2 pi, because it's a pure number, is just 1. So you have dimensions of 2 pi as 1, and dimensions of t, which is just the time, will just be capital letter T divided by the dimensions of t, which is a period, will just be t, where this cancels out with that. So dimensions of this argument are equal to 1. So this simply means that the dimension of its argument is equal to 1. This simply means that this trig ratio, which is the sine 2 pi t over t, is dimensionless. And when a quantity is dimensionless, it simply means that the dimensions of the entire quantity, sine 2 pi t over t, will also just be equal to 1 because it is dimensionless. Therefore, in this case, the dimensions here will just be L times 1. So the dimensions of the whole of that will just be equal to L. So now this has been satisfied. Rule number 5 has been satisfied. So we therefore remain with just satisfying the first rule, which is that left-hand side must be the same as right-hand side. So you check on the left-hand side, the dimensions are capital letter L, and on the right-hand side, dimensions are capital letter L. So left-hand side L, right-hand side L. So this equation is dimensionally correct, or it is homogeneous. And this is how we use dimensional analysis to check whether an equation is homogeneous.